Alright, so I keep writing down that we can tell something about the momentum of an object given its wavelength and vice versa. And this is a really important equation relationship that's called the de Broglie relation. And it's exactly related to this thing that we call wave-particle duality. And actually de Broglie presented it as his PhD thesis, which he had a very hard time getting accepted. It had a hard time passing his PhD defense, in fact. So what we have here is the basic idea of something we call wavelength. Lambda is the symbol, and if you think of a wave as just an up and down sine type function, the wavelength is defined as the distance between the repeat distance of the wave. So we have an upward lobe, a positive lobe of a wave here, and then a downward lobe of a wave, and the wavelength goes from the zero crossing as we go up toward the positive, and then to the next zero crossing that's also crossing from negative to positive. So that full span is called the wavelength. Now the de Broglie relation says that this wavelength lambda is going to be related to the momentum of the object when we think about it as a particle, and it's an inverse relationship, so the wavelength is this constant, Planck's constant, divided by, again, the magnitude of the momentum. The direction doesn't enter in, but the magnitude of the momentum is what you need to know. So the wavelength lambda equals Planck's constant divided by the momentum, and alternately the momentum is equal to Planck's constant divided by the wavelength. You can work it either way. Now we also keep running into this thing, h, which we call Planck's constant. It keeps cropping up. It's essentially the fundamental constant of quantum mechanics. So it's probably about time to define the thing. Now h is 6.626 times 10 to the minus 34 joules times seconds, so energy units times time units. Like almost everything in quantum mechanics, it's an incredibly small number. Most of the time you just need to use h. Every now and then we actually need to run the math and use the MKS units of h there. We're also going to turn out to run into h divided by 2 pi all the time. We use it so much that we give it its own special name, h with a slash across the stem of the h. We call h bar. And again, that's h divided by twice times pi. So again, let's review these funny quantum atomic units that we're going to use a lot in the class. They're pretty straightforward again, so the mass, we're going to deal in what we call the atomic mass unit, and once again, one atomic mass unit, 1 AMU, is 1.66 by 10 to the minus 27 kilograms. That's an amazingly small amount. I mean, it's the mass of one hydrogen nucleus. Now technically, the 1 AMU is defined as 1/12 the mass of a carbon nucleus, so it's 1/12 of a C12 nucleus. The next thing we care about is the charge that we keep repeating, and once again, the elementary charge is E. E is 1.6 times 10 to the minus 19 coulombs. Again, a really, really tiny number. Electrons are negatively charged, so they're charged with negative E. Protons are positively charged, so they're charged with positive E. And opposite charges attract, so we'll see that has a huge amount to do with the way that atoms and molecules behave. Okay, so now here's the big red disclaimer. Quantum mechanics it's really a story of things that are just incredibly small. They're very, very small, very fast, and very light. They have really nothing to do with your own personal experience. No observation of hockey pucks or things on a swing or anything from your fundamental intuition is going to have anything to do with the way that quantum objects behave. And so you just need to throw it away. We're going to build up intuition about how quantum things behave based on some very, very simple postulates, but you have to suspend disbelief and just throw away your intuitive notion for how things should behave to really get things out of the class. So this is the disclaimer. I should really fast and say all the other things that are in the fine print that you don't have to worry about when I'm all said and done, but just take a breath and follow along and enjoy the ride. Another of the wacky things that we pointed out when we were going over the properties of our quantum objects is probably the most completely quantum mechanical property, which is the spin angular momentum. that we call S. Now this thing is essentially an intrinsic angular momentum that fundamental objects, fundamental particles have, and it's called spin because you can think that maybe this thing is somehow spinning around. That's just an intuitive name. It doesn't really have anything to do with reality. Spin isn't really going to emerge for a couple of months, but when it does, it's going to be incredibly important. So just sort of file that one away, and we'll get back to it in quite some time. Okay, so let's think about wavelength again, but specifically with light, because light's the easiest way to think about wavelength. We're used to that one. Now remember that the wavelength of light is related to its color. It's this period of one electromagnetic wave, and we typically measure it in nanometers. So 1 nanometer is 10 to the minus 9 meters. And in the visible spectrum, light with a wavelength of about 420 nanometers is the shortest wavelength, highest energy light we can see is about, we call it the violet, and then you go all the way to about 700 nanometer light, and that's deep, deep red light. So from 420 nanometers to 700 nanometers is the wavelength range of the light spectrum that we can actually see. Now, in addition to wavelength, as I say, with units of nanometers, there are other ways that we measure the properties of the light. One thing we can do is we can just flip the wavelength over, and so instead of 1 over lambda, we have this thing we call a wave number, and we indicate that with the symbol nu with this funny little twiddle on top of it. So nu twiddle is the wave number. It's 1 divided by the wavelength, and typically the units we use for wave number are inverse centimeters, or 1 divided by centimeters. We can also think of the frequency of the light, and that's just regular old nu without the twiddle. And you get the frequency by taking the wave number, nu twiddle, and multiplying it by the speed of light, c. Alternately, you get the frequency by taking the speed of light and dividing it by the wavelength. Either way works. So we're going to refer to the properties of wavelength and wave number and frequency interchangeably by using these conversions here a lot during the class. So we've got these wonderful photon wavy light things that are waves, but they're actually also particles, and there's some pretty important consequences of that. We've already discussed the fact that photons have momentum, even though they don't have any mass. They've got momentum. They bloody well better have some energy, and the energy of photons, in fact, is quite fundamental. And since they come in chunks, it turns out that the energy of one photon at a frequency nu is given by our good friend Planck's constant times that frequency nu. So this relation here, E equals h nu, is one of the really fundamental relations of quantum mechanics. And you can file that away. So E equals h nu is the energy of one photon at frequency nu. And the other big equation that we learned in this segment is the de Broglie relation that tells us that the wavelength of an object is equal to Planck's constant again divided by the magnitude of the momentum of that object.